It's my great pleasure to introduce Jay Labov. Jay has had a tremendous influence in many, many areas of STEM education through his role as a senior advisor to the National Academies on educational initiatives for many years. I think he's been involved in probably all the reports that I've been involved with in one way or another for the Academies, but many, many others. And so Jay is currently retired, and I really appreciate him taking the time out to come and share some of what he's sort of seen from the broad report perspective that the Academies have brought to bear on educational initiatives and what it means for us in this context. So Jay, thanks so much. And feel free to go ahead and share your screen.
Okay, thanks, Lou. Before I do that, what I'd like to get a sense of who's in the audience. If you are an undergraduate, graduate student, or a postdoc, could you go down to where it says participants and then just raise your hand? I'm just curious to see what percentage of people are not faculty. Okay, not many people here are students. That's okay, because let me go and share my screen. Okay, what Lou has asked me to do is to talk to you about the future of graduate quantitative education, the topic of this workshop, but to use it from a broader perspective. So as Lou said, I worked for 23 years at the National Academies of Sciences, Engineering, and Medicine, focusing on ways to improve STEM education. And I did so at the K-12 undergraduate, graduate level, and did some international work too. And so what I'd like to do is, rather than focus on the particulars of what happens in individual kinds of courses, which has been extremely enriching, I want to give you a broader perspective, to be thinking about this from the perspective of students and the questions that they're asking. So what happens when I get out of my program? How do we connect quantitative education to things beyond graduate school, to teaching undergraduates, to possibly being involved in some way, either as volunteers or maybe as a career choice in K-12 education? And thinking about the other kinds of perspectives or career pathways that people might want to be taking into public service, into government, into industry. And I'll be talking about some of the data that relates to all of this. And the fact is that the world is really changing. And so we have to be thinking about, ultimately, as Joshua Weitz was talking about, a student perspective here. So the good news is that going last, you can kind of hear everybody and begin to figure out how to build on things. The bad news is that it also forces you sometimes to change your PowerPoint presentation at the last minute and sort of think about things differently. So I actually came up with this other slide. So what I want to do is to talk about something completely different than what we've been talking about here thus far. Okay, so I want to start with getting you to think about the future of graduate education in quantitative analysis and other aspects of the work that you do. And the reason I'm saying this is because just last week, November 12th, 13th, and 19th, the National Academies put on a very large seminar that was attended by literally hundreds of people. I participated in this, called Imagining the Future of Undergraduate STEM Education. And what they asked people to do is to help shape the vision and priorities for STEM education in the future. And their question is, what should be our ambitions for 2040? We hear a lot of what's going on right now in the programs that people have been talking about, but how do you think about this for 20 years from now? What is it that you really want to do, and what's the trajectory that you really need to get there when it comes to your programs and related programs? And what do we need to do to achieve that? One of the themes which permeated all of this discussion, which happened over these 3 days, is the need to increase diversity in all aspects of STEM and the kind of education we provide. And they thought a lot about different ways to do that. We won't have time to get into all of the details of that, but what I want to emphasize is that part of what we have to be thinking about, and people have brought this out in a couple of previous talks, is that the diversity in this area, it tends to be lacking in many ways. And what one of our priorities should be, I think, is to figure out how over the next 5, 10, 20 years, we're going to begin to address and resolve these kinds of questions. Okay. Now, some of you have already shown pictures of these kinds of things or mentioned them in the chat. There are a whole lot of different kinds of reports that have come out. The one that's in the center here on the roundtable on data science was published just this year. Data science for undergraduates and opportunities for integration of simulation science and data science from 2018. The role of theory in advancing 21st century biology, which obviously is quantitative, has a quantitative underpinning to all of this. It was 2014, if I remember. And issues like health literacy and numeracy also take the aspects of what you're interested in and trying to relate it to additional fields. And I think this also gets to the idea that we need to be thinking about what are the broad picture views that we're going to be having of what the world of work and academic and societal challenges that our students will be facing between now and 2040 and beyond. So all of these are National Academies reports. They're all available for free downloading at this website, nap.edu. And indeed, all of the Academies reports that I'm showing you will be freely downloadable at all of these at the same website. All right. I also attended in January. I was invited to speak on some of these broader contexts of data science, in this case, at Stony Brook University. And what you see is that what they were trying to do over the course of several days was to review the national landscape on major online resources for learning and teaching, lay out initial plans for developing frameworks for doing curricular design, facilitating learning environments, and laying the foundation for university industry collaboration on developing and disseminating case studies on data science. So here they were beginning to think more broadly than the academy. They were beginning to think about how industry relates to this. And I would say this is a good start, but we really need to be thinking even more broadly than that. And a couple of people have already talked about the idea of interdisciplinary approaches, and I'll have more to say about that. And I think this is the right track that we should be thinking about as we think about what the future holds. All right. Lou has mentioned a couple of times, and I just simply lifted this from his webinar presentation that he did in March prior to when we were supposed to be gathering in Tennessee, excuse me, of training fearless biologists, quantitative concepts for all our students, which came from the 2003 report from the National Academies called Bio 2010, Transforming Undergraduate Education for Future Research Biologists. And you can see that even in this report, these are the sorts of things where data and quantitative analysis could all be important to various aspects of undergraduate biology education. Now, I should also mention that before I went to the National Academies, I was on the faculty, a tenured member of the faculty department at Colby College in Maine for about 18 years. I'm kind of old. And what we were finding there is that when we ask our students why they become biology majors, unfortunately, too frequently, what too many of them said was, I don't like math, and biology is the way I could engage in science and not have to deal with mathematics and quantitative stuff. If I wanted to do that, I'd become a chemistry major or a physics major. And we more or less reinforced that issue. We really didn't bring up math very often at the time. I'm hoping that this is changing. But Biology 2010 is really beginning to give the kinds of topics that could be integrated very easily into various kinds of biology courses, rather than seeing the quantitative aspects as something separate. Okay. In 2009, the Board on Life Sciences at the National Academies produced the new biology for the 21st century, ensuring the United States leads the coming biology revolution. And if you remember, the context here is that the human genome had just recently been published. There was all kinds of work that was going on after the development of high-speed computing, on visualization, on a lot of data mining, and a lot of other things. And so what this report tried to do was to pull all of this together. And what they said is that at the time, the time offered a moment of unique opportunity because of the increasing integration of subdisciplines within biology, cross-discipline integration. And notice what they have here is that cross-discipline integration is really only within the natural sciences. I'll have more to say about that. Technological advances are enabling biologists to collect data unprecedented in quantity and quality, the data mining aspects, and past investments are providing value beyond what was expected. So where the Human Genome Project cost a couple $2 billion, now with 23andMe, you can get your entire genome analyzed for under $100. And so the amount of data that can become available because of these decreases in cost are things that provide unique opportunities. All right. What they also said is that if we think about the educational aspects of this, the new biology initiative that they were talking about provides opportunity to attract students to science who want to solve real world problems. And the question becomes, when we think about the programs that you're all involved with, how can this aspect of trying to solve real world problems begin to attract students who might not otherwise be interested in showing people that the quantitative aspects and data mining and opportunities for visualization can really begin to help people solve problems in ways that they never thought possible before. What they said is that the new biologist, as they defined it in this report, is not a scientist who knows a little bit about all disciplines, but a scientist with deep knowledge in one discipline and a working fluency in several. That doesn't mean that if you're an undergraduate, you major in biology and you take a course or two in chemistry and a course or two in physics. What this means is that you really are delving more deeply. Quantitative aspects of this should be part of what we think about here for scientists with deep knowledge in one discipline and a working fluency in several. It shouldn't just be in those other subject areas. I think the kind of work that you're all doing needs to be incorporated into this too. The question is, how do we go about doing this, and how do we increase that, and how do we integrate it in ways that we can attract students who might never have thought that this is the kind of thing that they wanted to do, that they became biology majors because they thought they were avoiding math rather than trying to understand how quantitative aspects is deeply foundational to what it is that they need to do. All right. They also said that highly developed quantitative skills will be increasingly important, and I've emphasized that here with a different color. Development and implementation of genuinely interdisciplinary undergraduate courses and curricula will prepare students as new biology researchers. Okay, and here again, I think the kinds of work that you're doing fits very, very well into what this was talking about. Graduate training programs that include opportunities for interdisciplinary work are essential. We have to begin to think about this not only because of the ways that quantitative biology is going, but because of the way that the world of work and the world itself is progressing. And programs to support faculty in developing new curricula will have a multiplying effect. In other words, if you can begin to, as one person talked about, sort of what's in it for other folks to become involved in all of this, enlightened self-interest, then what we can begin to do is to develop these programs in an integrated and interdisciplinary way that will attract people whose skills separately are not as much as they can be when we have synergism. All right. Here's another report that was published, one of the last ones that I worked on before I left the Academy in 2018, on graduate STEM education for the 21st century. And there are a couple of important things here that I think also mirror some of the things that were talked about earlier today. All right, for one thing, it's really important to understand that the majority of students with graduate degrees no longer pursue careers in academia. And so the question now becomes, graduate education, especially at the Ph.D. level, primarily prepares people for research careers in academia. How do we begin to reconcile these things? The fact that people are voting with their feet, and I'll show you some data very quickly in a minute that reinforces this. How do we begin to think about the fact that many, many people are not going to be staying within academia, And given the way that academia is going, particularly now after the pandemic and the travails that higher education is experiencing economically and in other ways, how will our students be best prepared to be able to do the kinds of things that they both want to do and need to do? All right. The improvement of graduate education in STEM is a systemic problem. A number of people have already talked about this in the chat and in their presentations and in the questions. How do you begin to think about what that department over there is doing and what their interests are, which may be orthogonal or anathema to the kinds of things that you're trying to do? How do you understand what their needs are so that you begin to develop a systems approach to this? And efforts to improve graduate education must be student-centered. And Joshua White's also pointed that out in his talk, that we have to begin to think more about how does graduate education for the 21st century benefit students as well as the kinds of things that we as researchers and educators are trying to do. Okay. Here's, I think, a pretty sobering thing that was published in Nature Biotechnology in 2013. And if anything, the issue has gotten even worse. So if you look on the right y-axis, what you see are annual numbers. And if you look on the left y-axis, this is in cumulative numbers. And what you can see is shown in blue, the annual PhDs awarded in the dashed lines and the cumulative PhDs awarded in science. But then when you look at the orange, what you see are the annual faculty positions and the cumulative faculty positions. And you can see right away that it doesn't take a lot of data visualization to realize that we've got a major problem here. And this only went up to 2011 when those data were available. If anything, the issue has gotten worse with regard to tenured faculty. So for over a long period of time, where the percentage of tenured faculty at most institutions was somewhere in the neighborhood of 40 to 45%. Now it's about 15%. And it may be going even less than that. So the question is, what is it that we have our students thinking about? And how are we preparing them for a world where tenured faculty positions in academia may actually become the alternative career pathway of the future? Because there will be so few positions that are available relative to the time that, or the number of people who are going into this and who we're trying to attract. And how can quantitative and the kind of quantitative education that you're providing help students think much more broadly about the opportunities that they have? All right. Here's also another thing about a shifting job market. For people like myself who spent an awful lot of my career working in the 20th century, on average, people had somewhere between 1 to 2 jobs, but it's predicted that the students who are undergraduate and graduate school now, by the time that they retire, and some people even think by the time they reach middle age, will have had somewhere between 10 to 15 different jobs or careers. So the whole model of how we predicate, how we educate is completely shifting in the 21st century, all right? And what I want to do is just shift for a moment. I'm probably going to have to get out of here and then get back in, but this is an interactive, and I'll show you a little bit of the interactive because of lack of time, from this website, which is from the U.S. Census Bureau. And if you just simply Google U.S. Census STEM workforce, you'll be able to get to it. So let me just get out of here for a minute and go into that website, and I'll be right back. Okay, so if you look at this, where do college graduates work? And what you can see is that you can change this so that you can look at all graduates. Can you see my cursor, by the way? All graduates, STEM majors, non-STEM majors. And what I have here are STEM majors. And when you look at that, you can also break this out by men, women, and various ethnic groups. Right now, these data are taken from people who are ages 25 to 64. They include people with bachelor's or higher degrees. And the field that is indicated here is what people said that they majored in, or if they majored in more than one thing, what they listed first. The database is of a couple million people. And so basically what you look at here is that if you look on the left-hand side, or where my cursor is, you can see all of these different professions or majors. And on the right side, where I'm moving now, are a number of different professions. Okay, so for example, if you hover over engineering, what you can see is the number or the percentage of engineering majors that are moving into careers after they graduate between STEM, which is in the upper right quadrant, and other kinds of occupations, right? And so about 50% of engineering majors are staying in STEM disciplines. But if you look at biological, environmental, and agricultural sciences, what you see is that the blue lines, which are showing the number of students who stay within some area of STEM, is pretty small. A lot of life sciences majors are moving on to other kinds of things. And if you now go over to the other side, and for example, you look at managers who are in non-STEM positions, you can see that there are people who are coming from the biological sciences, business and financial, a few, healthcare, quite a few. But even down here in legal, so in other words, there are people who are going in all different kinds of directions. And the question is, how are we preparing them, including those people who go on for their PhDs or masters and then decide not to stay in academia? How are we going to be preparing them? All right, so let me get out of here, and I'm going to get back into my PowerPoint. Okay. And you can go and play with this yourself if you want to take a look at the data a little bit more. We just don't have enough time. Okay, so in the idea that we have 1 to 2 jobs primarily as the model in the 20th century and 10 to 15 jobs in the 21st century, the job requirements are completely different. In the 20th century, we're talking about mastery of one field, but in the 21st century, critical thinking across disciplines. And how is it that quantitative biology can help students do that? The teaching model was subject matter mastery in the 20th century, but now integration of 21st century skills. And by 21st century skills, some people sometimes also refer to those as the soft skills. I call them more the hard skills, because what we're talking about are people who are able to deal with each other, people who are able to ask original questions, people who can actually analyze complex data, who can work with other kinds of people, who can communicate effectively and use their data in ways that allows them to communicate effectively. All right, we're not going to worry about the assessment models, but I think you begin to see that what we have here in the 21st century is, given the realities of the workplace and the fact that students are voting with their feet, as we showed you before, that we have to begin to think differently about this. And so as we have this trajectory toward 2040, what is it that we need to be doing to think about what we're doing now and how we might change that and how we might improve it and how we can make it more student focused? All right. These are 2 other reports that came from the Academies on convergence. The major one in 2014 on life sciences, physical sciences, engineering, and beyond. And again, what we're talking about primarily are the STEM disciplines. And here's in 2019, fostering the culture of convergence in research. But the sciences extend far beyond just the science. Their reach extends far beyond just the scientists themselves. And so you notice that the bottom of this report that was published of the cover of this report that was published in 2018 says branches from the same tree. This is a quote from Albert Einstein, who basically said all areas of knowledge are branches from the same tree. And so this report is the integration of humanities and arts with science, engineering, and medicine. Things like data visualization and the kinds of work that a lot of your students are doing within the sciences can help them tremendously in thinking about careers along those kinds of lines, for example. This report is really important because if you go to the website for NAP and go down to resources, you'll also see a couple hundred different programs which have been highlighted in a database, in an Excel spreadsheet that gives you an idea of all of the different kinds of programs that are going on here. So as you're thinking about interdisciplinary programs here, how do we begin to also include our colleagues in the in the social sciences and in the humanities? Because the kinds of social issues and societal issues that our students are going to be facing and helping to address in the future, by necessity, are complex enough that they have to extend beyond the sciences. All right. Another question is the whole notion of using data for communication. This is published about 6 years ago now, but it came from AAAS. And it's the gaps between AAAS scientists and engineers and the public on biomedical science topics. So in other words, for example, they were people who were not scientists or engineers were asked, is it safe to eat genetically modified foods? And then people who were members of AAAS were asked the same kind of question. What you notice is that in so many of these questions, is it safe to eat genetically modified foods? Do you favor the use of animals in research? Is it safe to eat foods grown with pesticides, et cetera? Have humans evolved over time? And should vaccines be required? There are considerable gaps between what the public thinks about and what scientists think about. I think this has certainly been manifest in everything that we're all dealing with now with the COVID issue and how people think about science and the role of science, or the fact that they don't think that science is very much involved. And the question is, how do we prepare our students to help resolve these kinds of issues? Because in many ways, they're existential issues. If we don't deal with people understanding, for example, the science of climate change and the role of scientists, we're in deep trouble. And so the question is, how can our students and how can we help our students to begin to think about this data visualization in ways that are coupled with communication, in ways that are coupled with effective teaching practices, for example, can all help our students in so many different ways, both in finding employment and in growing professionally. Okay, so I would say that the future of undergraduate education, which I focused on a lot, depends on the future of graduate education. But I would add a corollary to this, and that is that the future of quantitatively informed students, members of the workforce, policymakers, and the public depends on the preparation of appropriately prepared graduate students. And my question would be to you, and that hopefully we can discuss in some of the breakout sessions, is are we doing that? And if we're not doing that, how do we begin to think more broadly about how to do it and the importance of doing it and engaging our colleagues, both in the administration and other faculty colleagues, as well as buy-in from our students. I'll finish with a quote that actually came from the American biology teacher in the September 2020 edition. And that is, this article is called using messy, authentic data to promote data literacy and reveal the nature of science. And what these authors said is that in addition to a specific abilities, such as being trained in visualizing, analyzing, and interpreting data, data literacy, quantitative literacy, is characterized by habits of mind, such as curiosity, resiliency, and ethical decision-making. And I think that last one is critically important, particularly in the places that we find ourselves today. How do we begin to help our students understand the need for the ethical use of data and how to transfer that kind of information in the workplaces and in other places where they will be interacting with others in their role as scientists? So I will stop there, and I thank you for your attention. And I know we don't have a whole lot of time for questions, but we can go to breakout sessions, and hopefully some of this will influence some of the things you're talking about. Thank you.
Let's thank Jay an awful lot for a quick summary of many key ideas and reports. Let's just see. Is there anybody want to raise their hand for a question quickly? Now's a chance to do it. Jennifer.
I have a question, or maybe a comment. You said that the future of undergrad education depends on the future of graduate education.
No. Yes.
I think also the reverse is true, because we source a lot of our grad students from undergrad programs. And so as undergrad programs, a lot of universities struggle with incoming students who may not be prepared for basic undergrad education. So they're struggling with retention issues, keeping a robust undergrad student body, meeting the needs of undergrads, especially like in times like these. That has a big impact also on our graduate programs. We try to lead with graduate programs, but it can be a real struggle depending on what's happening in the undergraduate world. So I was just wondering if you could comment on that.
No, I fully agree with you. As I said before, it's a systems problem. And so it's not only at the undergraduate level, but it's at the K-12 level, and it goes beyond that. What I was referring to is, and I should have said a little bit more about that, is that when I think of graduate students, they are in essence, the analogy would be pre-service teacher education. In other words, our graduate students are the future faculty. And ultimately, what we have to begin to do is to think about how do we prepare them to be effective faculty, particularly in teaching. And I should also point out, we just didn't have enough time, that 50% of the nation's undergraduates right now are in community colleges. Community colleges, for the most part, are not involved with research. And so those people who go there are going to be teaching the most diverse group of students that we have in the United States. They have many, many other kinds of issues. They're not the typical undergraduate. The 19-year-old undergraduate who goes for 4 years or 6 years is pretty much fading out at this point. Other reports we did at the Academies certainly point that out. But my point is that we need to think about graduate education as a pre-service education program for future faculty. And if we don't begin to do that, then what we do is we spend endless amounts of time, effort, and money in trying to re-educate faculty into things like active learning, into things like we know there's a vast literature out there about what works. But for the most part, we never help our graduate students or postdocs really understand any of it. And so they kind of have to figure it out themselves. And unfortunately, and I felt victim of that. I didn't know there was a literature until I went to the National Academies about how people learn. I mean, it's crazy, in many ways, it's almost like malpractice. If you're a neurosurgeon and you were working on somebody's brain for 3 hours and you didn't know anything about the brain, you'd be out on your keister very quickly. We work on students' brains for a whole semester. And
I feel like as faculty, this also puts a lot of expectations on us because the field is moving quickly.
Yes.
We are the ones training the grad students, and we need to stay at least as current as they're going to be. And so we are constantly on this edge of re-envisioning ourselves and recreating ourselves constantly because we're expected to be training graduate students to be really effective in an evolving, situation for jobs, for example.
Yeah, but many professions are evolving in medicine and law and, in academia. And so if people see it as part of their ongoing professional development job responsibilities, but it's a systems problem. How do we make those opportunities available, particularly now when people have just been essentially cast out onto the ocean to do, online learning and teaching with very little preparation, But we have to begin to think about what will happen after we finally get back to what might resemble normal. There will not be the same normal. And so how do we begin to think about that trajectory and as they say in hockey, skate to where the puck is going to be?
Okay.
So we have to begin to anticipate.
Yep. Yeah. Thanks, Jay.
Thanks, Jennifer. I want to give Jan had his hand up, and I want to give him a chance if he wants to say something quickly, and then we'll go to breakouts after.
All right, thank you. Great presentation. I wanted to think about the idea that all the disciplines in STEM are different branches of the same tree. And what separates us is mostly language and constructs that we have developed over time. And so I believe that there might be value in teaching at different level some sort of epistemology. Is the fundamental of the question is like, how do we know what we know? And how do we approach that? And how the scientific method has emerged from this question. So trying to go back to the roots of the tree and give all the students in STEM this fundamental knowledge about, what is it that we do in science and how do we approach it? and then how is that diversified into all the branches and all the things?
Sure. Yeah, so I completely agree with you. Again, it's a matter of time. Somebody was talking about coverage before. To me, somebody told me the hallmark of the effective educator is not what they cover, but what they uncover. And so what we have to begin to think about is another aspect of this, particularly for things at the undergraduate level, let's say in introductory courses, what's most important 5 or 10 years out? Because for most undergraduates, an introductory course is not an introductory course, it's a terminal course. It's the last thing that they'll take. So is it more important that they've memorized the Krebs citric acid cycle, or that they know the difference between the first and third law of thermodynamics, or is it they understand what a controlled experiment is, and that they understand that there is no one scientific method? And ultimately how, as you're saying, how do we know what we know? What's the process by which this happens? But for too much in both textbooks and in our teaching, that's kind of pushed to the side. We kind of assume that people have learned some of that in K-12. For the most part, they haven't. I could go on and on. We don't have time, but it's very clear that most of our students really have no appreciation of these kinds of things. I saw it in my seniors at Colby College. The creme de la creme of biology majors really had no clue.
Thanks a lot, Jay. Again, and I know we're going to have quite a bit of conversation on many of these issues, and thanks to Natalie as well for a stimulating set of comments.